Welcome, students. In this video, we are going to study the following worksheet on continuity. Let's start. First problem, let's find the intervals where f of x is continuous. Let's start by checking this point x is equal to 1. Limit as x is approaching to 1 of x squared minus x over x squared minus 1 is equal to limit as x is approaching to 1, x minus 1 over x minus 1 multiplied by x plus 1. So that limit is equal to 1 over 2 then. So this two-sided limit is not equal to the value of function at point 1, meaning that our function is not continuous at point x is equal to 1. Next, here we see a rational function and it is continuous everywhere with the exception of zeros in denominator. And the zeros that we have in denominator are 1 and minus 1, meaning that our function is continuous everywhere except those 2 points, minus 1 and 1. So here are the intervals where f of x is continuous. In the next problem, find the numbers at which f is continuous. Right? At which of these numbers is f continuous from the right, from the left, or neither? Okay, let me copy down. All right, so let's recall that our function is continuous from the left of some point if limit as x is approaching to point A, let's say from the left, is equal to the value of function at that point. And it is continuous from the right if we are approaching some point A from the right, and the value, this limit is equal to the value of function at that point. Okay, so let's start. First, let's check this point 0. Limit as we approach to 0 from the left is equal to 1. Our value of function at point 0 is equal to 1. Limit as we approach 0 from the right is equal to 2, meaning that function is not continuous. So function is discontinuous at point x is equal to 0. However, since a limit as we approach to point 0 from the left is equal to the value of function at that point, it means that it is continuous from the left at point 0. Anyway, so let's start writing down the intervals where our function is continuous. Here we see a polynomial, it's continuous everywhere. So first interval where f of x is continuous is from minus infinity to 0. And at 0 we have discontinuity. Next, 2 minus x is again a polynomial. It is continuous everywhere. So now let's check point x is equal to 2. Limit as we approach to 2 from the right side is equal to x minus 2 squared, and that is equal to 0. Limit as we approach x to 2 from the left side is equal to this limit here, and is also equal to 0, meaning that our function is continuous at point 0. And this is polynomial, it's continuous everywhere. And that is also another polynomial, it is continuous everywhere. And we checked point 2, meaning we have shown that our function is continuous at that point. Since two-sided limit exists, two-sided limit here is equal to 0, and value of function at point 2 is also equal to 0, since if we substitute 2 here, we'll get 0. So conditions for our function being continuous at point 2 are satisfied, meaning that the intervals where our function is continuous is from -infinity to 0 and from 0 to +infinity. Okay. Now, next problem. Find the numbers at which f is discontinuous. Again, same question. Let's copy that somewhere else. Okay, again, we are starting with a polynomial. It's continuous everywhere. Now let's check point x is equal to 0, limit as we approach to 0 from the left is equal to 2, limit as we approach x from the right is equal to 1, meaning that we have discontinuity at point 0. Next, e of x exponential is continuous everywhere. So now let's check point x is equal to 1, limit as we approach to 1 from the left side is equal to e, and limit as we approach to 1 from the right side is equal to 1. Okay, so we can see that we have another point where our function is not continuous at x is equal to 1. Next, we are followed up with polynomial that's continuous everywhere. So 2 points where our function is not continuous are 0 and 1. Now let's check these points and let's see whether our function is continuous from left or right. Now, point 0. Value of function at point 0 is equal to 1. And we have seen that limit as we approach point 1 from the point 0 from the right side is equal to 1, meaning that at 0, our function f of x is continuous from right. Okay, next, let's check point x is equal to 1. And we can see that when we are approaching to point 1 from the right, from the left side, its limit is equal to e, and the value of function at point 1 is also e. So at point x is equal to 1, at point x is equal to 1, our function is continuous from the left. All right. Okay, next problem. For what value of the constant c the function f is continuous everywhere? So we have a couple of polynomials, they are continuous everywhere. Now let's check point x is equal to 2. Limit as we approach to 2 from the left side should be equal to the limit as we approach 2 from the right side. So this is x cubed minus cx. So we have a 4c plus 4. That should be equal to 8 minus 2c. So 6c is equal to 4c is equal to 2 over 3. Then for value c is equal to 2 over 3, our function is going to be continuous everywhere. Okay, next problem. How would you remove the discontinuity of f? In other words, how would you define f at point 2 in order to make f continuous at 2? So we have rational function. It's continuous everywhere, except zeros of denominator. Let's expand this as x minus 2, x squared plus 2x plus 4. Denominator, we have x minus 2 multiplied by x plus 2. So at point x is equal to 2, we have removable discontinuity. Okay, and a limit as we approach point 2 is then equal to, we are taking limit of that. If we substitute 2 here, we'll get 4 plus 4 plus 4, 12, 12 over 4, which is 3. So making f at point 2 being equal to 3 is going to remove discontinuity at 2. However, we should notice that our function has another discontinuity at point x is equal to minus 2. It's not removable discontinuity. Function blows up here since that polynomial has no root x is equal to minus 2, so they won't cancel out. To remove discontinuity, however, at point x is equal to 2, we simply have to make the value of function to be equal to 3. Okay, the last problem from this worksheet. From the graph of J, state the intervals on which J is continuous. At point minus 4, we can see that our function is continuous from the right. So the limit as we approach to this point minus 4 from the right is equal to the value of function at that point. So interval left boundary here should be closed. It is continuous from minus 4 to point minus 2, where we have jump discontinuity. On interval from minus 2 to 2, we see that our function is continuous. At point 2, we again have jump discontinuity, and it is not continuous from the right, I mean from the left. At point 2, since the limit as we approach to that point from the left is not equal to the value of function at this point, since the value at point 2 is defined over here. Okay, now we can see that it is continuous from the right at point 2, since the limit will be equal to the value of function at that point. Then we see infinite discontinuity at point 4. Then it is continuous up to point 6. At point 6, we have jump discontinuity, and it's not continuous from the left at point 6, and it's also not continuous from the right at point 6. So right boundary here and left boundary of that interval, they will be open. And at point 8, we also see that the value of function is not defined at that point, meaning that it's not continuous from the right. Okay, so here we see the intervals where our function g is continuous. All right, guys, now that will conclude our review of worksheet on continuity. Thanks for watching.